Good morning. In this lecture we will discuss the methods of preparation of haloalkanes. So there are mainly three methods that haloalkanes can be prepared from alkene, can be prepared from alkenes or from alcohol. So first we will start from alkene. How the haloalkanes are prepared from alkenes. So in alkene, suppose we have a CH2 ethene. When you add a halogen acid like HBr, it will give you CH3 CH2 Br. Simple method. This is a type of first thing is, this is a type of electrophilic addition reaction. If you see the mechanism of this reaction, that involves formation of carbocation. Okay. So what is the mechanism? First of all, this CH2 double bond CH2 is ethene, is electron-rich species. It has a pi electron above and below the plane. This is a pi bond here. So when H positive is added first, H positive is electrophile, so this ethene will act as a nucleophile because it is an electron-rich species. So this when hydrogen H positive come close to this ethene, so one of the pi bond that shift in this direction, that negative charge, this get positive charge, this negative attack on electrophile. So to produce CH2 CH3, positive charge will be on this carbon. It becomes CH2 plus this hydrogen 2 from CH3. This is your intermediate carbocation. This is the first step. In the second step, what happened? This carbocation, this is ethyl carbocation, and we have a Br negative ion, this one HBr. So this Br negative easily attack on it to produce bromoethane. So this is the overall reaction. Why it is called electrophilic addition reaction? Because electrophile is added first. Br negative to add हो ही नहीं सकता because Br negative is a electron-rich species and this ethene is also electron-rich species. So Br negative ion cannot come close to this carbon-carbon double bond. There will be repulsion. So H positive will first add it to produce carbocation and carbocation के ऊपर फिर attack कर देगा हमारा halide ion to produce the haloalkane. Now in case of symmetrical alkenes, it doesn't matter that this pi bond shift in this side or this side. But in case of unsymmetrical, it will matter. For example, let's see some examples of this reaction. Now suppose we have a, say, but2ene. This is also a symmetrical alkene. Doesn't matter that double bond shift to which side. When you add HBr, you will get 2-bromobutane, or you can say it secondary butyl bromide. Secondary butyl bromide. In this case also it doesn't matter that this pi bond shift in this direction or this direction because both sides are equal. Because the symmetrical alkenes doesn't matter. So, for example, if we have alkene like this and adding HBr, again you can add on this carbon or this carbon, anywhere you can add Br or H. you will get a bromocyclohexane, one bromocyclohexane. Say you add Br here, H here. So because this is also a symmetrical alkene, it doesn't matter. Now, if the alkene is unsymmetrical, if your alkene is unsymmetrical, like CH3, CH, double bond CH2, this is propene. This is your unsymmetrical alkene. Now, when you add H positive, first step, there are two ways. Either this bond shift in this direction, say it's A, or it move in this direction, say it's B. So you will get two different, you can say, if it moves toward A or B, two different carbocations are produced. अगर ये A की तरफ जाएगा तो यहाँ पे नेगेटिव आ गया, नेगेटिव विल अटैक ऑन दिस, तो पॉजिटिव चार्ज सेंटर वाली कार्बन पे आ जाएगा, CH3, CH पॉजिटिव, CH3. अगर ये B की तरफ जा रहा है पाई बॉन्ड, तो H यहाँ अटैच हो जाएगा और पॉजिटिव चार्ज एंड वाली कार्बन पे आ जाएगा. So in this way you get two carbocation. Okay, this is your 2 degree carbocation, and this is 1 degree carbocation. 2 degree carbocation is more stable. You know that 2 degree carbocation is more stable. It means this is formed in large amount, in excess. Then, when the Br negative attack on it, it will give you CH, Br. So this will be your major product. Major product means main product. One bromo propane बनेगा, लेकिन that will be in very small amount, negligible amount. So कहाँ पे इलेक्ट्रॉन को शिफ्ट करना है, पाई बॉन्ड किस साइड जाएगा, you can detect from these two the stability comparison, or you can detect from here also. How? This is a methyl group, it is electron donating. So when it is electron donating, अगर ये इलेक्ट्रॉन इसको दे रहा है, इसका मतलब ये पाई बॉन्ड इस तरफ तो नहीं आएगा. ऑब्वियसली नहीं आएगा तो फिर जाएगा किधर, ए साइड, तो वही प्रोडक्ट बनेगा. तो फ्रॉम हियर यू कैन आल्सो डिटेक्ट. नहीं तो आप दोनों कार्बोकेटाइन ड्रॉ करो, देखो कौन सा ज्यादा स्टेबल है. तो ऐसी रिएक्शंस अगर आपको आ जाए, सपोज उसने लिखा है CH3, CH डबल बॉन्ड CH2 प्लस HBr और बोल दिया कि मेजर प्रोडक्ट लिख रहे हैं, तो आप क्या लिखोगे, मेजर प्रोडक्ट की जगह पे सेंटर वाली कार्बन पे आप लगा दोगे Br. इसका एक रूल भी है कि इसका नेगेटिव पार्ट डबल बॉन्ड की उस कार्बन पे लगा दो जिस पे हाइड्रोजन कम है, दैट विल बी द मेजर प्रोडक्ट. ओके, नेगेटिव पार्ट ऑफ अटैकिंग reagent, that is HBr here, will add to that carbon of double bond which has lesser number of hydrogen atoms. That will give you the major product. Okay. So simply अगर मेजर प्रोडक्ट बोला गया तो आपको HBr कहाँ लगाना है, Br को कहाँ लगाना है, जिसके ऊपर हाइड्रोजन कम है. इसी को हम बोलते हैं मार्कोनिकोव रूल. Same thing, same this statement is covered under Markovnikov rule. Markovnikov. इसको सिंपली आप मार्क डाल के डॉट लगा दो, मार्क रूल बोलते हैं। ये रूल क्या कहता है कि इन केस ऑफ unsymmetrical alkene, when halogen acid like HBr is added, उसके बाद स्टेटमेंट आ जाती है यहाँ, द नेगेटिव पार्ट ऑफ द टैकिंग एजेंट विल एड टू दैट कार्बन ऑफ द डबल बॉन्ड which has lesser number of hydrogen atom is known as Mark rule. तो सिंपली इन अनसिमेट्रिकल में, सिमेट्रिकल में तो कोई फर्क ही नहीं पड़ेगा, अनसिमेट्रिकल में ये काम करेगा। जैसे मान लो मैं एक एग्जांपल दे रहा हूं, आपके पास ये है, इसमें HBr ऐड करना है, तो बोल रहा है राइट द मेजर प्रोडक्ट। पहले देखेंगे कार्बन ऑफ डबल बॉन्ड कौन कौन सी, ये कार्बन ये है, ये कार्बन ये है। ऊपर वाली कार्बन के पास हाइड्रोजन नहीं है, नीचे वाली कार्बन के पास एक हाइड्रोजन है, तो फिर आपका प्रोडक्ट क्या बनेगा, Br कहाँ लगाओगे, डबल बॉन्ड चेंज इनटू सिंगल, है ना, यहाँ पे पहले से मिथाइल है, तो यहाँ पे आप लगा दो Br। सो दिस इज योर मेजर प्रोडक्ट। ओके, so this rule is called Markovnikov rule। अब जैसे मान लो क्वेश्चन आ जाता है, how will you convert isobutene to tertiary butyl bromide? तो कॉमन नेम बहुत ही जरूरी है, आपको कॉमन नेम करने पड़ेंगे, नहीं तो समझ में नहीं आएगी बात हो क्या रहा है। आइसोब्यूटीन होता है CH3CH, ओके, सॉरी C हियर, CH3 डबल बॉन्ड CH2, टर्शियरी बुटाइल इसमें HBr ऐड कर दो, तो Br कहाँ लग जाएगा, CH3Br। So this is your tertiary butyl bromide. So when carbocation is formed, as an intermediate, then rearrangement is possible, रीअरेंजमेंट में क्या होगा, या तो हाइड्राइड शिफ्ट मीन्स H नेगेटिव, या होगा मिथाइल शिफ्ट, CH3, या होगा रिंग एक्सटेंशन। तो ये देखेंगे कैसे होता है। अब मान लो हमारे पास जो अल्कीन है वो है ये, this is you can say 3-methyl but 1-ene. Okay, now when you are going to add H positive to it, so obviously this will move in this side, it's a negative, because in this side there are electron donating groups are there, attack on it to produce CH3C, CH3H, CH positive, CH3, This is a 2-degree carbocation. It rearrange. How it rearrange? There is a hydride shift. Like this hydrogen along with electron that moves here. This is called hydride shift. H negative shift to produce another carbocation which is 3 degree, and 3 degree carbocation we know is more stable. Then on this 3 degree carbocation Br negative attacks to produce the final product. So this is your major product. So this such type of reaction you can complete only if you know about the rearrangement. Rearrangement generally take place if we have a 1 degree, it will move toward 2 degree, it will move toward 3 degree. Not in reverse direction. We will move towards more stability. Okay. Same is methyl shift. For methyl shift, I am taking another example like this. When you add H positive, it produces carbocation. Okay, this is again your 2 degree carbocation. Now this carbon is 3 degree. अगर इस पे पॉजिटिव चार्ज आ जाए, that will become more stable. Now the methyl shift is there. पूरा group CH3 along with electron that moves. So CH3 shift इसको बोलते हैं methyl shift. It produces CH3C positive charge here. CH3, CH, CH3, CH3. This is your 3 degree carbocation. Is more stable. Then what next? Next is adding Br negative here to produce. So this will be your major product in this case. There is also methyl group. Okay. So after rearrangement you will get this product. Third is about the ring expansion. If the carbocation is formed adjacent to 3-membered, 4-membered ring, suppose we have this is a alkene, and when you add H positive, it will give you positive charge here, 2 degree carbocation. This is your 2 degree carbocation. There may be hydride shift to produce 3 degree carbocation, but if there is a ring, there is a ring expansion. Like this carbon, these 2 electrons, they add this, and positive charge will appear on this carbon because these electrons are moving. So we get 5-membered ring with methyl and positive charge on adjacent carbon. Okay. Then what next? Next is adding Br. It is added here to produce this. So this is known as a ring expansion. So when carbocation is formed, these 3 things are possible: either hydride shift, methyl shift, or ring expansion. Possible means जरूरी नहीं कि होगा ही होगा. कई बार कार्बोकेटाइन बनेगा लेकिन उसमें रीअरेंजमेंट पॉसिबल नहीं होगी. पहले अगर वो स्टेबल है, मान लो 3 डिग्री है, तो फिर उसमें रीअरेंजमेंट जो है वो नहीं होगी. नेक्स्ट थिंग इज व्हेन यू एड, now suppose we have CH3, CH double bond CH2, तो इसमें आपने ऐड किया था HBr, ये बन गया था CH3. Major product is your isopropyl bromide. Now we are adding HBr in the presence of peroxide. Peroxide is like ROOR. H2O2 भी हो सकता है, वो भी peroxide है. Then product formed is against the Markov rule. This is your major product. This is called Mark rule, we know. But this is your anti-Mark rule. Or this is also known as peroxide effect. This is also known as crash effect. It takes place only in the presence of peroxide. Because when peroxide is there, the mechanism changes. Here the mechanism is electrophilic addition. Here the mechanism become free radical addition, because peroxide produce free radical. So what is the mechanism of this anti-Markov rule? Any peroxide that undergo homolytic fission, और हम उसको बोलते हैं homolysis. And when there is a homolytic fission, one electron, it produces free radicals. Two free radicals are produced. Now this free radical that will first combine with HBr, like this RO free radical combined with HBr. So it forms a bond like this to produce ROH plus Br free radical. Okay, and this Br free radical can also combine with another Br from HBr to produce Br2 and H2. Sorry, H radical. Now Br radical is added first to the double bond because that's more electron deficient. Suppose we have this propene and we are adding a Br free radical to it. So there are again two ways. Either the Br is added on this A or it is added on B. If it is added on A or if it is added on B, what products are formed? See, if it is added on B, free radical will produce at. So if it is added at A, you get this thing. Free radical is present on this carbon. If it is added to B, free radical is like we are adding here. Then free radical is produced here. See, this is your 2 degree free radical. And this is your 1 degree free radical. This is more stable. Then what happened next is adding H radical here to produce CH3, CH2, CH2, Br. This is your major product formed. So this is called anti-Markov or peroxide effect or crash effect.